We have learned about various properties of a binary operation on a set. Now, depending on how many of those things are satisfied, we have different names for them. Suppose I have a set S together with a binary operation on it. Because we shall be working with such a pair again and again, we have a convention of writing this like this. So, the first element is always a set and the second one is a binary operation on the set. Now, if it is just this, a set together with a binary operation, which means by default that I am assuming closure property alone and nothing else, then this is called a groupoid. So, just this, that means it is a groupoid. Now, you should understand that the less number of properties we put on this binary operation, the more general is the structure, the more abstract is the structure. But at the same time, the more abstract the structure is, more difficult it is to work with. For example, if there is no associativity, then obviously you can't do anything with this particular operation. The concrete thing as well as the abstract thing both must move along the same line. So, a very general structure is not very useful. At the same time, if you put too many conditions, then that will also not very useful because it is not general. It will be specific to one example. So, we have to strike a balance between them. So, we keep on putting more and more conditions. If we put too many conditions, that is bad because that will not generalize many different situations. If we put too few conditions, that is bad because we cannot do much manipulation. So, we put the next condition, which is associativity. If that is the case, immediately we get a more useful thing which we call a semi-group. Pretty useful thing. If further we have the existence of identity, then we get what is called a monoid. If on top of that we also have existence of inverse for all the entries, then we have a group. If on top of that we also have commutativity, then we have what is called an Abelian group or a commutative group. So, these two things are quite general, at the same time they allow for lot of manipulation. So, these are very popular structures. This is less popular and basically unpopular. So, our lecture will focus on this and this. There are many different examples of groups. The simplest example possibly is Z plus, which means the set of all integers together with addition. You can very easily check that this is a group. We know that it is closed, that is, if we take two integers, then the sum is again an integer. So, if I take m and n in Z, m plus n is again in Z, that is closure. Associativity, that is the property of addition, we already know that. So, for all m n p in Z, m plus n plus p is same as m plus n plus p. Similarly, if I have the number 0, that is the identity. So, for all n in Z, 0 plus n equal to n plus 0 equal to n, that is the identity. and the inverse, role of the inverse is played by negative of a number for all n in Z, n plus minus n is again in Z, equal to minus n plus n, that is equal to 0. So it's a group. Not only that, it is an abelian group or a commutative group, because for all mn in Z, m plus n equals n plus m. Now, if you understand this, it should be quite easy to see that even if I replace this with Q, the set of all rationals, that also works. If I replace it with R, that also works. If I replace it with complex number C, even then it holds. But will it hold if I replace it with set of all natural numbers 1, 2, 3, 4, etc.? The answer is no, because even this property fails. Because, this property does not fail, because if I take two natural numbers and add them, then that's again a natural number, but this property fails. I do not have any 0 in the set of natural numbers. So there is no natural number such that if you add that to any natural number, you get back the original number. Okay, to remedy it, I might try the following. Say I take this natural number union 0. So it's 0, 1, 2, etc. Now, of course, there is no problem with this property, but still we can't work, because this will now fail, because natural numbers do not contain, natural number union 0 does not contain any negative number, so inverse will not exist. However, if I work with this, this fails and all the rest remains, so I have a monoid. If I remove this, then I have a semigroup. It will be a commutative semigroup or a commutative monoid if I allow 0. Now, is this a group? Let's try. Z together with minus. So, for all mn in Z, m minus n, yes, that is in Z. If you take two integers and subtract one from the other, you still get an integer. Will this work? This minus, well, we know that this does not hold in general. For example, if I take 1 minus 2 minus 3, that should be minus 4, and that is not same as 1 minus 2 minus 3, which is 2 minus 3 is minus 1, minus of that, so this is 2. This is 2 and this is minus 4. So they are not same, so this property fails. Again, this property also fails, because 0 minus n is not same as n. So in this way, this is not a group. A different type of group is given by the unit circle in the complex plane. So we are in the complex plane. This is the unit circle centered at the origin. Then we know that every point on the circumference may be encoded as e to the power I theta, where theta is this angle. So every element here is this e to the power I theta. So I will take S as this unit circle, and I will take the operation as complex multiplication. So this is multiplication in C. So if I take two entries here, e to the power I theta 1 and e to the power I theta 2, I multiply, then I get e to the power I theta 1 plus theta 2, which means I get this is theta 1 and this is theta 2. So if I multiply, then basically I add theta 1 plus theta 2 and I move to some other place. So since it is again of the form e to the power I times some real number, so we have another point on the circumference. And when I keep on adding, they will wrap back. So after this 360 degree, they will come here and it will continue to go like this. It will never move out of the circle. So that is an example of a group, because I already see that it's a binary operation, it is closed. And that it is associative is the standard fact about multiplication in C, because we know multiplication in C is associative. To prove that, you just have to expand the entire thing and check. And then we have to see that this has an identity element. This element is 1. 1 is the identity which lies in the circle. And inverse is not very difficult to see that identity element is 1, which is e to the power I 0. So if you take any e to the power I theta, consider the corresponding e to the power minus I theta. Multiply them, then theta and minus theta will cancel and you will end up with just e to the power I 0, which is 1. So it is actually a group. Not only that, we know that multiplication in C is commutative, so it is an abelian group. Now here is another example of a group, a more exotic one, and it's like this, that I start with any set. To give a simple example, my set is A, 1, 2, 3. So the set doesn't really have to be finite or anything, but I am giving one example which is simple. Now consider its power set. By power set, I mean all possible subsets of the set, including the empty set. So it contains, if there are 3 entries here, the size of the power set will be 2 to the power 3, that is 8. So there is the empty set, that's a subset of A, the singletons, the doubletons, and the entire set. So these are my power set of this. The collection of all these sets is the power set of A. That is my set S. So I am giving you a group, so I need to give you a set together with a binary operation. The binary operation will be this, which is called symmetric difference. So symmetric difference between sets. Remember, the elements of S are actually sets, subsets of A. So the way symmetric difference is defined is like this. Suppose this is my S and these are 2 subsets. So this is my set, which is A in this case. These are 2 subsets of A. Subsets of A are elements of the set S. Then the symmetric difference between them is defined as those elements in M which are not in N, union those elements in N which are not in M. This is the symmetric difference of M and N, and we write it as M, the triangle N. Let's take an example and you will understand. Suppose I am trying to find symmetric difference between 2 and 3. So I will take all the elements in this set which are not here, well, there is no such element, and all the elements which are here but not here, there is only 3. So the rule is you cancel out the common elements and see whatever remains. Similarly, if I say 2, 3 and 1, 3, their symmetric difference will be you cancel out the common elements, 3, you are left with only 1, 2. That's it. Now if that is the case, let's see whether this is a group, that is whether S delta is a group or not. The first condition to check is whether it is closed. Of course closed, because I am working with all subsets of A. Since I am talking with all subsets of A, by taking symmetric difference I will get some subset of A, so it must be again inside this. Secondly, is it associative? Well, that requires quite a bit of checking, but you can do it directly. So you have to write down both the expressions, the left hand side and the right hand side, and painstakingly check everything, and you can show that yes, it is associative. Proving associativity generally is just hard work, because that is actually the property which is the most liberating property. So that is, to prove it, you have to put quite a bit of effort there. Then comes existence of identity. That is not very difficult. The set such that it will not change even if I take symmetric difference with a specific set. Empty set is going to play that role. So if I take, say, 1, 2 and I do symmetric difference with empty set, remember, I will be cancelling out common elements. So if I do not do any cancellation, then I am just left with whatever I was having originally. Now you will cancel common elements, but since this is an empty set, there is no common element, so you will not do any cancellation. So this is just your original set, and it is also an Abelian operation, a commutative operation. What about inverse? So inverse means something such that if you take symmetric difference of a set with that, then you will be left with nothing, which means you are cancelling off everything. You want the result to be just the 5. So I had 1, but 1 is not there in the result, which means 1 has been cancelled off. Why can 1 be cancelled off? Only if you have 1 here also. Similarly, 2 has been knocked off, so 2 must be here also. Should there anything else be there? No, because had there been anything else, that would have remained here, because that will not be the common element, which immediately shows that given any set, any element of capital S, that is any subset of A, it is its own inverse. Every one is its own inverse. And that shows that for any set A, power set A together with the symmetric difference operation is an Abelian group. We are moving towards more and more exotic examples of groups. So here is one which doesn't involve any number at all. We have already seen this. So I take an equilateral triangle cut out of cardboard and I create a frame to fit it into. So I have this equilateral triangle which has the numbers 1, 2 and 3 written at the 3 ends, 3 vertices, and I am also leveling the ends of the frames with them. My aim is to lift it up and put it back again on the same frame such that it fits perfectly. The question is, what are the different ways by which I can put it? I can just put it directly, I can turn it 120 degrees in this direction, that direction, I can flip it, and in this way we had 6 different ways of putting them, and they were, I called L, which means turning 120 degree left, turning 120 degree right, not doing anything, that is E, and I can flip. There are 3 possible flips depending on the axis of flipping. If the axis passes through the one of the frame like this, then it is F1. If it is 2, F2, and if it is like this, then it is F3. Remember, my F3 is determined by the 3 written here, not the 3 written here. So if I start like this and I say that you give it a right rotation and now apply F2, you do not flip keeping this fixed, you flip keeping this fixed, the 2 of the frame, so you move like this. Now the operation that I will be talking about here is what I had mentioned earlier. I denoted it by the heart shape. This is followed by or and then. So if I say L F1, which means you first apply L, follow it with F1. So you first apply L, I start like this, I first apply L, follow it with F1, so I apply this, I am left with this, so it is 2, 3, 1 and it is flipped, and here I can see that 3 is at the right place, so it will be F3. So had I done just this, I would have also arrived at the same position, so it will be F3. I claim that the set of all these 6 things, so S, which is E, L, R, F1, F2, F3 together with this operation forms a group. First of all, it is a binary operation. That should be obvious, because how did I get these 6 operations, or how did I get these 6 objects? Because I listed all possible ways by which I can place it back. Now, if I can place it back fitting on the frame after one move, and I follow it with another move which also keeps it fitted into the frame, then they together will continue to keep the triangle fitted on the frame. So, I am sure that the final result must be one of these 6, because these are all the possible things that will allow the triangle to fit into its frame. So, closure is just obvious. Now I have to check associativity. Well, associativity you might have difficulty in checking, but if you remember that function composition is associative, then it will follow immediately, because when I say L, I mean that I am applying a function on this. Consider this position and I am applying some change, so it's a function. And then I am following it up with another function, and I am considering the composite effect. So this is actually function composition in disguise, and function composition happens to be associative. So that is why this will be associative. So you may need to think a bit about this point. Now, what is the identity element? The identity element is, of course, E, do nothing. So if you do L and then do nothing, that is L. You do nothing and then you apply L, that is L. So that is the identity element. The inverse, that should be pretty easy. L, what is its inverse? You want to get back to the original configuration. Inverse of L is R. Suppose you have flipped it and you say, oh, I should not have flipped it. What should you do in order to get back to your original thing? Flip it again. Similar. So F1 inverse is F1, F3 inverse is F3, F2 inverse is F2. And what is inverse of E? Doing nothing. Well, its inverse is just itself. That is again E. Is it Abelian? Well, I leave it for you to check that it is not Abelian. So here's the exercise of the day. Try to come up with 2 elements such that they do not commute. So try to come up with 2 elements, x and y. They are elements here such that x heart y is not same as y heart x. If I take x equal to L and y equal to R, that's not going to work, because L heart R and R heart L will be both same as E. So try to do this, and we will continue in the next video with more such examples.